I'm Cheng from BAI. It's my great honor to be here. Today I will introduce our new research called Code as Monitor. It's all about helping robots detect failures before and after they happen. A little bit about me. I'm a researcher at Beijing Academy of Artificial Intelligence, focused on embodied AI. I've published over 20 papers in the AI area with more than 3,700 citations. Feel free to reach out by email or check out my website if you are interested in my research. Okay, this was a team effort. Here is the author list. Our paper will be presented at CVPR 2025. Check out our project website for demos and more details. The full paper is on Archive 2. First, let me introduce the motivation of our work. At present, Internet AI based on web data has achieved relatively good results, but embodied intelligence that learn from interactions is still in its early stage. So why do we need failure detection in embodied AI? In embodied AI, agents interacted with complex environments over long periods. Failures are difficult to completely avoid. Even the SOTA model, such as Pi-Ling, Pi-0 model, and RVT2 model makes a variety of mistakes. A robust system must detect and handle failure effectively to ensure task reliability. So what should we expect for an ideal failure detection framework? Currently, most of failure detection work based on VLM will detect the error after it occurs. We call it reactive failure detection. As shown in the picture, we need to take the pot with lobster from the table to the stove, and we can only detect it after the lobster fell out. Do we have to detect and recover after failures occur? We defined a new failure detection type. It can detect foreseeable impending failures and prevent them from before they occur. We call this type proactive failure detection. In our research work, we hope to unify the two failure detection methods in one framework. First, we unify these two methods into a spatial temporal constraint satisfaction problem. As the reactive type, the framework checks whether the required states of entities, such as robots, objects in the environment, are reached at the end of the task. As for the proactive type, the framework checks whether all entities in the environment maintain the required states during the task. Then we're using the reasoning and generalization of VLMs to convert the open set failure detection into a set of spatial temporal constraints. Additionally, we use codes to accurate and real-time evaluate whether the entities maintain the required states during the process and reach the states in the end. In order to accurately characterize the spatial temporal constraints, we propose a new representation called constraint element. Constraint element abstract constraint related entities or their paths into geometry elements such as points, lines, and surface, which are composed of points in 3D space. In the upper right corner of the slide is an example of a constrained element, including using 3 points to represent the plane of the port and using 2 points to represent the distance between the gripper and the port handle. So what is the advantage of constrained element? First, 3D points are convenient as code input for calculation. Second, constraint element abstract constraint related entities and remove environment geometry and visual elements. Third, real-time monitor can be achieved by simply tracking and constraint element and calculating their spatial-temporal relationships. Next, let me introduce the whole framework. Step 1, constraint generation. We use GPT-4o to act as a constraint generator. We input the task instruction, previous subgoal, and current multi-view observations. Constraint generator outputs the next subgoal and the textual constraints. Then the second step is paint constraint element. Constraint painter converts textual constraints into constraint element and paints them on multi-view images. In this step, we introduce a reasoning segmentation model called concept to do the instance level and the party level segmentation. For example, the textual constraint may be the pen should remain horizontal during transfer. Please segment the desired parts. Concept not only segments the related pen plane, but also outputs the constraint type, that is, it needs a surface. The second step is voxelization, clustering, and varying. Point clouds are fused according to the camera internal and external parameters and depth information. Then we voxelize according to the constraint element type. Voxel grid is clustered and the point number is issued according to the constraint element type. All points are connected within the object to obtain the constraint element in 3D space. Then we project the constraint element in 3D space back to the image view. The third step is monitor code generation. We input the textual constraint and the visual prompted images into GPT-4o to generate monitor codes. When the task is executed, the code will calculate the constraint states in real time. If a constraint is not satisfied, a failure reason will be returned and the current subgoal will be restarted. Let's have a look at the experiments. We conduct the experiments in 3 simulators, including clipboard, Gypsum, and RL bench. We also conduct real-world experiments. Due to the time constraints, I select some interesting experimental videos. The first one is the task of inserting a pen into a pen hole. During the task execution, we will artificially introduce interferences, such as moving the position of the pen before grasping it, forcing the pen to fall after grasping it, and moving the position of the pen hole before inserting the pen. Our system will robustly response to the interface and accurately complete the task. The second one is to stack blocks in a certain order. We will deliberately make the position of the blocks so that the stacked blocks will fall easily. Our framework can quickly detect failures and re-execute the task until it succeeds. In the first real-world experiment, the instruction we give is to clear all objects on the table except for animals. During the task execution, we also change the position of the target object and remove the object from the textual hand. And our system was able to respond stably. The second real-world experiment is to grasp the animal according to their distance to fruits, from nearest to farthest. There are two animals and two fruits on the table. We will frequently change the position in the process, thereby changing the target object, and our system can easily handle it. Here is more demonstration of our consent model. This demonstration shows the generalizability of our consent models. Here is the position of our booth. Welcome to have a nice talk. That's all. Thank you.